Swayam Prabha. Digital India. Educated India.
Hello friends, we are back with the second lecture where we are discussing about the reactor control or basically the way of controlling a nuclear reactor, where we have started with discussing the role of neutrons and particularly the role of prompt and delayed neutrons separately, and also the reactor kinetics. Now, anything related to the nuclear reactor always comes down to how the neutron behaves inside the reactor, or how can we control the behavior of the neutron inside the reactor. And accordingly, the topic of reactor control is also essentially related to controlling the neutron profile or neutron flux distribution inside the reactor, both its variation with respect to space and also with respect to time. Just a quick recap of the first lecture. There you are initially introduced the concept of fuel burn up, where which refers to the amount of fuel consumed by inside the reactor over a period of 1 day, and we have seen that the fuel burn up for nuclear reactor is significantly smaller compared to a thermal reactor, and that is why once we have loaded a reactor with a certain quantity of fuel, we can keep on running for a very long period, which can range from several months to more than a year. Then we discussed about prompt and delayed neutrons. It was already introduced in earlier modules that prompt neutron is the one which is the immediate product of a fission reaction, and therefore, it appears within 10 to the minus 14 second of a fission occurrence. However, delayed neutron is the product of the radioactive decay of certain neutron rich fission fragments. Like we have seen that while beta decay is the most common type of radioactive decay that fission fragments undergo, there are certain situations where some certain neutron rich isotopes appear, and they also need to have a certain amount of energy, that is the energy level of the concerned nucleus rather should be higher than the binding energy of a single neutron. Then it can also undergo a neutron decay and thereby contributing that delayed neutron. Delayed neutron can appear significantly after a significant time after the appearance of the actual fission. That time may vary from a few milliseconds to more than a second. Like probably the longest living delayed neutron precursor has a half life of around 55 seconds, and that is why there can be wide variety of delayed neutron precursors that may be present inside a reactor, and accordingly delayed neutrons can become available in different period of time. But first we discussed about the prompt neutron lifetime, and there we have seen that it is generally a summation of two components, the scattering period and also the diffusion time. Generally the scattering time is significantly smaller compared to the diffusion time, and hence for particularly for thermal neutrons we can blindly take this LP, that is the prompt neutron lifetime, to be similar to the diffusion time, and it is generally of the order of 10 to the minus 3. For fast neutrons there is no scattering component, so it is only the diffusion time, and that is the diffusion of the fast neutron, and that is generally of the order of 10 to the minus 7. Then we discussed about the prompt neutron kinetics. Considering a single group neutron model, we have developed this particular equation which shows if n naught is the initial number of neutrons present inside the reactor, that is at time equal to t equal to 0, this will be the transient profile of this nuclear reactor or transient profile of neutron inside the reactor, where LP is the prompt neutron lifetime and K infinity is the multiplication factor, or it can directly be related to this reactivity as well. And as LP is of the order of 10 to the minus 3 commonly, the reactivity when that is of the order of 10 to the minus 3, we have seen that just within a period of 10 seconds this number of neutrons can become, like when I am saying when reactivity is of the order of 10 to the minus 3, we can see that this reactor time, that is LP divided by rho, is of the order of 1, and in that case at just a time t equal to 10 seconds, total number of neutrons can be e to the power 10. That is, it can increase extremely sharply, and the rate actually is too high to get controlled by any kind of practically available machineries. Therefore, if there are the entire kinetics of a nuclear reactor is depending solely upon the prompt neutron, then the control of the reactor becomes extremely critical. Just with the reactivity of the order of 10 to the minus 3, we are seeing such an exponential rate of growth. Just think about what may happen in a fast reactor. In case of a fast reactor, LP is of the order of 10 to the minus 7, and therefore, this even when the reactivity is 10 to the minus 3, this NT will be N naught into exponential of 10 to the power 4 for just a single second, and that is impossible to control. Therefore, it is we can conclude that the reactor which is depending solely upon the prompt neutrons, the control of that is extremely critical, and in most of the cases practically impossible. But thanks to the role played by the delayed neutrons, we often find a way, actually much easier way of controlling the reactors. Easier way means basically we have always have much more time to do any kind of operation, to operate our control equipments, because that is because of the role of the delayed neutrons. That role we have roughly discussed, and we have seen this is the way the delayed neutron that is produced, with the examples of some delayed neutron precursors we have seen, like it is for barium 87 is given, which is the immediate product is krypton 87, and while most of the cases krypton 87 undergoes a beta decay, in certain situation it can also undergo a neutron decay, but only if when this particular isotope has significant amount of energy which is higher than the binding energy of a single neutron. And then we went to the delayed neutron kinetics, which we only started in the previous lecture. As a part of the delayed neutron kinetics, we have adopted a 6 group model. Basically, there can be so many number of delayed neutrons that can be present in a single fission reaction or can appear during following the chain of a single fission reaction. We often combine these neutrons into a few groups, or we club them into a few groups, and the most preferred approach is to follow 6 group kind of thing. Like these are the groups for uranium 235. For every group, the corresponding parameters like the decay constant, the fractional yield for this, these are all averaged over this, and hence instead of considering the constituents for each group, we can just take all of them together. Like for uranium 235, the first group can have a value of beta, which is a fraction corresponding to this group divided by the total number of neutrons prompt plus delayed that may appear following a single fission. It is extremely small. You can see for the first one it is just 0.00215, that is just 0.0215, and the total delayed neutron fraction that we can find is 0.0065 for uranium 235. It is different for different other fissile isotopes, but our discussion we are mostly keeping restricted to uranium 235, and so this combined value of beta is important to remember, which is 0.0065. Now, we shall be taking the delayed neutron kinetics forward. These are the equations, just remember these are the equations that we developed during the previous lecture. Here n refers to the neutron density, and the rate of change of the neutron density can have different components such as the neutron produced following the fission, that is the prompt neutrons which may appear because of a fission reaction, the delayed neutrons which may appear because of the radioactive decay of the delayed neutron precursors, and also there should be neutron absorption. Combining all, we got this particular equation. Here instead of considering the 6 or 8 different groups of delayed neutrons, we are just considering all of them to be clubbed into a single group, and the concentration of that group is given by C, and the coefficient corresponding parameter values for the group are taken as single lumped values, like lambda is the decay constant which is representative of the entire group. and the same is applicable for beta and k infinity and others. The second equation dc dt represents the rate at which the concentration of the delayed neutron that changes. Here the first term on the right hand side represents its rate of production and second one represents the rate of decay, the same. Now, let us assume k infinity to be equal to 1 and rho to be not equal to 0 for t greater than 0. That is, we can consider at the beginning, that is when you are starting our analysis, the system is working under a steady state and it is critical. So, its k infinity is equal to 1 and rho is equal to 0. Now, there is a step change in reactivity, that is the reactivity changes by a very small amount, and the change in k infinity is so small that we can neglect it for most of the calculation purpose. But rho is a very small positive quantity for which we are going to do this analysis. So, putting these expressions and rearranging the terms, we are here where just remember we assumed a solution of this form n equal to a e to the power omega t and c is equal to b to the power omega t. Here a and b are two coefficients and omega is the frequency. So, this is a single matrix equation that we have got, and we have to find a solution for this one in this particular module. So, this particular set of equations, these two equations can have a solution or a non-trivial solution only if the determinant of this one is equal to 0, and from there we are getting this, the determinant will be the this particular component multiplied by this minus this particular one multiplied by this one. So, this has to be equal to 0 in order to have a non-trivial solution for this matrix system, and then we are simplifying the terms, that is we are multiplying the first with omega and then with lambda and then combining the terms is, and whatever we are getting now we are rearranging into a form of a quadratic equation where omega is the variable and we are having LP into omega square plus this quantity in the bracket into omega minus rho lambda as the third term. This is like any quadratic equation can always be represented as a omega square plus b omega plus c equal to 0. In that case, the solution of this equation, there will be two solutions, should be equal to minus b plus minus root over b square minus 4ac divided by 2a. So, the same thing is done here. Here if we follow the equation, capital A refers to LP. Actually, I have used I should have used capital B here. This is capital B, this is capital A and C, and this also is 2 of capital A. So, in this equation, capital A refers to LP, B refers to this underlined quantity, and C refers to minus of rho lambda. So, we put them together and then we got the solution for this omega. Here of course, the plus minus sign appears, which represents two different solutions or two different values of omega, one corresponding to the positive one and other corresponding to the negative one. And a bit of further rearrangement where this squared quantity is coming out of the root and we are having an expression like this for omega. So, now we are taking couple of assumptions. First assumption is beta minus rho is significantly larger compared to this product of LP and lambda, and the second one is beta minus rho plus LP whole square of that is significantly larger than 4 LP into rho into lambda. Actually, the second one can be obtained from the first one, like if you think beta minus rho is greater than LP lambda. So, if we add LP lambda on both sides, then becomes twice of this, and now if I take a whole square of this, should also get a whole square of this quantity or should be greater than this, or in a way we can say if we are taking a whole square of the first one, it should be greater than whole square of this, or beta minus rho plus LP lambda whole square should be greater than or significantly greater than 4 into LP lambda whole square, or we can just say it has to be greater than 4 into LP lambda. And rho is a quantity which is generally very small positive number, at least as per our consideration. So, multiplying this particular term with rho will make it even smaller. But of course, the first approximation, that is beta minus rho is significantly greater than LP into lambda, is something that we shall be proving later on using the magnitudes corresponding to uranium-235. For the moment, let us proceed forward with these two assumptions. This is if I go back to the previous slide quickly, here now this numerator of this quantity is significantly smaller compared to the denominator. So, we can write this one as 4 LP rho into lambda into beta minus rho plus LP lambda whole to the power minus 2, and then if we expand this one following whatever way we could like to do, as LP lambda is significantly smaller compared to the first term, then compared to the LP lambda, then we are having an expansion of somewhat this particular form, and then we can have two roots from this, one corresponding to the positive sign and one corresponding to the negative sign. If we take the positive sign, then beta minus rho plus LP lambda, this and this one cancels out, and what remains, that if we simplify is of a form like this. And to proceed further, beta minus rho is significantly greater than LP lambda as per our assumption. So, if we put that, the first root for omega is coming to be rho lambda divided by beta minus rho. Similarly, if we take the negative sign here, then the expression for omega 2 is somewhat like this, and there we can use again the first assumption that we had, beta minus rho has to be significantly larger than LP lambda, and if we simplify, omega 2 is having a solution like this minus 1 upon LP into beta minus rho. So, we are getting two solutions for omega 1 and omega 2 because of the quadratic nature of the original equation. Now, remember earlier solution that we have assumed is n is equal to e into exponential of omega t, and similarly c is equal to b into e to the power omega t. But here we can see that omega can have two values, omega 1 and omega 2, and hence the solution of n and c has to be such an additive form. It is a 1 e to the power omega 1 t plus a 2 e to the power omega 2 t for n, and this should be b 1 e to the power omega 1 t plus b 2 e to the power omega 2 t for corresponding to c. And we can also write this in this particular form, where instead of omega we are writing at 1 by capital T, where capital T is the corresponding time period. Omega again we thought about as the frequency or the angular frequency, and capital T is the corresponding time period for this. Now, omega upon omega 2 then has to be equal to T 2 upon T 1. These are the expressions for omega 1 and omega 2 that we have derived shortly before, and if we put those expressions, then T 2 upon T 1, the magnitude of that comes to be LP rho lambda by beta minus rho whole square. But in the previous slide only we have considered beta minus rho to be significantly larger than LP into lambda, and once you multiply the two with rho being a small number, this has to be significantly greater than LP lambda into rho, and hence we can safely say that this T 2 has to be significantly smaller compared to T 1, or omega 1 is significantly smaller than omega 2. Therefore, though we are getting two frequencies and two different characteristic time constants, but one of them is dominant over the other one, or I should say significantly dominant over the other one. Now, we need to justify those two assumptions that we have considered, or particularly the first assumption, that is beta minus rho is significantly greater than LP into lambda. If we consider uranium-235 as the nucleus, then we can say that LP lambda product, LP is of the order of 10 to the minus 3 seconds, and lambda corresponding to uranium-235, that is the average value of lambda decay constant, for all possible delayed neutron precursors that may appear with iridium 235, that is just 0.08 second inverse. So, the product of lambda and LP is having a dimension of the order of 10 to the minus 5. Beta, now for uranium 235 beta is 0.0065, that was shown earlier also, and let us say the rho is 0.002. Rho 0.002 we are going to consider here. Then beta minus rho is something like 4.5 into 10 to the minus 3, that is beta minus rho is of the order of 10 to the power minus 3. On the contrary, LP lambda is of the order of 10 to the minus 5, and therefore, we can clearly say that beta minus rho is definitely much larger than LP into lambda. And the going to the second assumption, now beta minus rho plus LP lambda whole square, if we put the magnitudes of beta rho and LP lambda into this, then this comes out to be of the order of 10 to the minus 5. But once we multiply this 4p lambda, lambda p into lambda into LP with 4 into rho, that comes out to be of the order of 10 to the minus 7. So, that shows that the second assumption, that is beta minus rho plus LP lambda is much larger than 4 LP rho lambda, that can be justified from here. Now, we start with an initial condition that where at t equal to 0, k infinity is equal to 1, that is the system was running in the critical condition and its reactivity there has to be equal to 0. Now, because of has to be equal to 0 and the initial concentration of the neutron is given as n equal to n naught and corresponding concentration of the delayed neutron precursors can be C equal to C naught. So, with these initial conditions, let us try to find a solution. These are the original equations that we already had, and once we put k infinity equal to 1 and also all the other steady state values to this, then under steady state dn dt or any time variable has to go to 0. So, this 2 goes to 0. This is the form that we get from the first equation, and this is the one that we are getting this from the second equation. Here we have of course put n equal to n naught and C equal to C naught and rho equal to 0. See, both the equations are very much identical and we can use any one of them to get relation between C naught and n naught of this form. So, we are getting C naught equal to beta upon lambda LP into n naught. That is, once we know the value of these 3 parameters beta, lambda and LP, which all of them generally are quite standard, beta equal to 0.0065 for uranium 235, lambda value was also known, which is the average value for of decay coefficient constant for combining all possible delayed neutron precursors, and LP is generally of the order of 10 to the minus 3. So, we have a relation between C naught and N naught. Now, you already know that this is the form of the solution that we had. So, in that solution, now we can safely put our expressions, that is at t equal to 0 of course. Once we put use t equal to 0 in this equation and put n equal to n naught and C equal to C naught, then e to the power omega 1 t goes to 1, and similarly e to the power omega 2 t also goes to 1 corresponding to t equal to 0. So, we have n naught equal to a1 plus a2. Similarly, this is also 1 and this is also at t equal to 0 is equal to 1. So, C naught is also equal to b1 plus b2. And again, these two conservation equations that we already had, like these are the two conservation equations that we had. The first one is the conservation of neutron density and second one is the conservation of delayed neutron precursors concentration. There, if we put the solutions, let us pick up the second equation, that is, let us pick up this particular one, and there we put these two forms of n and C. This is not a t equal to 0 I am talking about, this is the general expression where we are putting n and C. Then this is the expression, original equation that we had, and once we put the expression, that is we integrate the expression for C and we are putting it here. Here actually we are not putting this particular equation, rather for simplicity we are putting the original equation, that is equal to a to the power omega t and C is equal to b to the power omega t. Then this is the form that we are arriving with, from where e to the power omega t can cancels out, and once we are cancelling out these terms, then by rearranging we can say that b is equal to beta upon LP into omega plus lambda into A. Now, we have to remember that there are two values of omega which we have identified in the previous slide. So, while we have used just a general expression of n equal to a to the power omega t and c equal to b to the power omega t in this expression to get a relation between a and b, we should put omega 1 and omega 2 separately into this, which should give you the relations between a 1 b 1 and a 2 b 2. So, that is what we are trying to do now. If we put omega equal to omega 1, then we are having a relation between a 1 and b 1. Similarly, if we put omega equal to omega 2, we are having relation between a 2 and b 2. Now, just try to remember what we have developed earlier. I hope you are deriving this also parallel to me. Omega 1 is equal to rho lambda divided by beta minus rho, and omega 2 is equal to minus of beta minus rho divided by LP. So, let us put this into this expression, put omega 1 here, which is rho lambda divided by beta minus rho. So, B1 simplifies to beta minus rho by LP lambda into A1. Similarly, putting the expressions of omega 2 into this, let me erase these writings from here as they are overlapping. So, putting omega 2 here, we are having a relation between B2 and A2 as B2 equal to minus beta by beta minus rho into A2. Now, we have already seen that C naught equal to B1 plus B2 and N naught is equal to A1 plus A2. So, use this expression for B1 and B2 into this, and also the relation between C naught and N naught that we have developed in the previous slide. If we put all of them, this is what we are getting from the first equation, as we have already derived C naught is equal to beta by LP lambda into N naught, and these two expressions for B1 and B2 we have just developed from the previous, just on the above. And now, N naught is equal to A1 plus A2. We can just add these two equations together by multiplying the second one with any suitable coefficient, so that we can get a solution for N naught in terms of A1 and A2, or a relation between A1, A2 and N naught. So, let us multiply this equation of N naught is equal to A1 plus A2, let us just multiply with this particular factor. Then we have beta upon beta minus rho into N naught equal to beta by beta minus rho into A1 plus beta by beta minus rho into A2. These two equations, now we add them together. Let us just this and we add them together. So, this cancels out. So, with A1 we can take these two common, we can take these two common to get a combined coefficient of A1 and then simplify. Similarly, we can add these two together to get a coefficient for N naught and get a combined expression which comes out to be a form like this. And once we simplify, A1 coming to be beta by beta minus rho into N naught and A2 equal to minus rho divided by beta minus rho into N naught. So, we are having a solution for A1 and A2 in terms of N naught. N naught invariably is a known quantity, because just try to think about how can you calculate the value of N naught. N naught refers to initial number of neutrons that can be present inside the reactor. So, that has to be a known quantity depending upon the generally just to initiate the reactor or initiate the nuclear reaction, we have to supply some kind of neutron. So, some source of neutron which we generally supply to initiate the entire process, and once we know the neutron supplying rate for that source, then we always have some information about this N naught. And other quantities like beta, rho and rho, which are the other two parameters that are appearing here, they are also generally known to us, because beta is a standard value for any given nucleus. Like for uranium 235, beta is equal to 0.0065, and rho is actually the parameter, that is reactivity, which we are trying to control through this entire exercise. So, we now have A1 and A2 in terms of N naught. So, once we put these two, we know that N is equal to A1 into e to the power minus in A1 into the omega 1 t plus A2 to the power omega 2 t. We are putting this expression of beta by beta minus rho into N naught exponential omega 1 to t, and the second expression we are putting, where we are putting the getting value of omega 2 t, and once we are rearranging the terms, this is what we are getting finally. Now, this is the final expression or final solution that we were looking to find through this entire exercise, that is n naught or expression for n as a function of time and its relation with n naught. Here it is found to be a combination of two exponential quantities. This is the first one and this is the second one. The first one actually this is e to the power of omega 1 t and this is the e to the power of omega 2 t. Now, if you remember, in the earlier slide we have proved that omega 1 is significantly smaller than omega 2, that is as per the assumption that we are considering, and therefore, the contribution for this second quantity that has to be much larger in deciding the neutron flux profile inside the reactor. And the first one of course, is at least when all the terms inside the brackets are positive, then the first one will represent a growing exponential term and second one will represent the decaying exponential term, but the role of second one has to be much larger as omega 1 is much smaller than omega 2. Now, omega 1 being such a small quantity compared to omega 2 as per our assumptions, let us completely neglect this term. In that case, n upon n naught is approximately equal to minus rho upon beta minus rho into exponential of minus beta minus rho upon L p into t. And let us just analyze this particular term. When beta is greater than rho, or I should say let us take the other case, when rho is greater than beta, when rho is greater than beta, then this quantity is positive and this is also positive, this coefficient of this entire coefficient, and so your profile, that is n, is actually a positive exponential function. So, it will increase exponentially. If we plot time on this axis and n upon n naught on the other axis, it will exponentially grow. That is what is the situation that we get for prompt neutrons as well. Just to put into perspective, for prompt neutron we also got a profile of this particular kind of form upon exponential is equal to rho upon L p into t, as rho and L p both are when rho is a positive quantity, L p being always a positive quantity, it was also a positive exponential, that is it showed a very steep growth. Yes. But now, with delayed neutrons the beta is coming into picture. The other situation, when beta is greater than rho, then this quantity is a negative one. So, it will show a negative profile of this, or n upon n naught if we plot with respect to time, then that will exponentially decrease, and hence we can have much we can maintain the reactor into subcritical condition as long as the reactivity is less than beta. Again, we would like to put into perspective with what we got in prompt neutron. In case of a prompt neutron, taking a rho value of 0.001, we can have n upon n naught the order of t, because L p is typically of the order of 10 to the minus 3 as well. And that is why when for a very small value of reactivity rho equal to 0.001, it is a straightforward exponential function of time and it increases very, very steeply. But with delayed neutrons, now with uranium 235, beta is equal to 0.0065. So, as long as the value of rho is, or this particular value is greater than the reactivity, the reactor growth will, or rather the neutron profile will keep on decaying. Only when this beta and rho becomes equal to each other, then we get n upon n naught is equal to 1 or is equal to the coefficient. Of course, it leads to rho by beta minus rho into e to the power 0, Yes. Of course, it leads to mathematically an impossible situation, because the denominator becomes 0 in this particular situation, but we can seek a solution for this from other means. But this represents that the rate of neutron growth will remain the same, and we can attain a critical situation for this. And this kind of situation, the reactor is called prompt critical. So, when beta and rho are equal, then only we call it prompt critical, and for uranium-235 beta equal to 0.0065. So, reactivity can be significantly higher than 0, significantly higher than that 0.001 or 002, which can be disastrous in case of only prompt neutron kinetics, but still we can have a safe operation going on. So, in a nutshell, the entire objective, or rather the concept of controlling a nuclear reactor using the delayed neutron kinetics is to maintain the value of rho quite close to beta or maybe less than beta, or I can summarize as rho has to be less equal to beta. For different nuclei, beta can have different values, and accordingly we generally one new unit of reactivity is often defined, which is called dollar. It is the same as the US currency, it is dollar. Dollar is defined as that value of reactivity which makes the reactor prompt critical. That is, dollar corresponds to that value of reactivity when rho becomes equal to beta. This is not an absolute unit, because for different isotopes beta has a different numbers. It is 0.0065 for uranium-235, but can be anything else for uranium-233 or maybe Pu-239, and hence the magnitude of dollar also keeps on varying, or the definition of dollar I should say keeps on varying. But whatever material, once we have fixed up one nuclei for fission reaction, then we know what is going to be the value of corresponding beta, and once we know the value of beta, then corresponding value of rho, or actually that particular number should be defined as $1. 1/100th of a dollar is often called 1 cent, just to be make the same kind of convention as in currency. So, that is all about the delayed neutron kinetics that we generally can have. We have I am keeping this lecture a bit short because we had lots of mathematics. I would urge you to do the entire derivation, and if you have any trouble, please write to me, we are there to help. But the conclusion that we can draw from today's lecture is that the role of delayed neutron is extremely important, though the quantity of delayed neutron that may appear through the during a fission reaction is extremely small. It is invariably less than 0.1%, but still that can play extremely important role in reactor control, and rather I should say that it is only because of the delayed neutrons we can develop a proper controlling mechanism. If there are no delayed neutrons, if all the neutrons appearing inside the reactor are of prompt in nature, it would have been impossible to control a nuclear reactor. It is only because of the delayed neutrons we can maintain them, maintain subcritical, critical or supercritical condition inside the reactor as per our choice. Yes. So, that is it for the day. I would like to keep it here itself, and in the next class we shall be discussing about other topics related to the nuclear control, where firstly I should be talking about the two most prominent mechanism by virtue of which we can control the reactivity inside the reactor, and hence the power profile inside, and also a few associated terminologies will be introduced. Thank you.